Swayam Prabha. Digital India. Educated India.
Hello everyone. In the previous class, we started our discussion on foundations on weak rocks. I gave you the idea that what all can be the problems associated with the foundations when they are founded on the rocks. So today we will learn about the determination of ultimate bearing capacity of the foundations, and we will be using Bell's approach for this purpose. All of you are aware of the fact that if the footing is to be founded on the soil, then two criteria should be met in order to have the safe bearing capacity of the foundation. What are those two criteria? The first one is that the footing should be safe in shear, and the second one is that the settlement of the footing should be within the permissible limit. Similar is the situation in case the foundation is to be placed or rested on the rock or rock mass. So let us try to learn about this Bell's approach first, and then we will proceed further with other methods in order to obtain the safe bearing pressure of footings resting on rock or rock masses. So this Bell's approach is based on classical earth pressure theory. You all must be aware of the active earth pressure and the passive earth pressure. So this theory or this approach is based upon all those concepts. So here there is going to be the consideration of equilibrium of two adjacent elements in the foundation material, and one element would be taken just beneath the edge of a strip foundation, and another one would be taken just outside it, and these elements would be taken at a depth z below the ground surface where the footing would be placed. Take a look at this particular figure. So here this is the footing which is placed at a depth of z below the ground surface. So this is your ground level, and from there at a depth z below you have placed the footing. So as I mentioned that we are going to consider two elements. One is just beneath the footing here and one is just outside it, and these have been shown here like this. So the zone which is immediately below the footing, that is this zone we call as active zone, and the zone which is outside this, which is this portion, this is going to be the passive zone. So just let us see that what exactly is this Bell's approach. So I just redraw this footing here, say this is what is your footing, and it is there at a depth of z, and these are the zones. So this is here you have the active zone, and here you have the passive zone, and these are all rock mass. this. Now, as I mentioned that you take a element here and take one element here just outside. So, what will happen? This is just below the footing. So, what is going to be value of sigma 3 here? That's going to be your gamma times z, where gamma is the unit weight. And see, although for clarity I am drawing it little bit below, but this element is just adjacent at this particular level only. And here we have sigma 1. Likewise, here you will have sigma 3, and for this element you will have sigma 1. Now, depending upon what is this rock material, which constitutive law that it is following, you will always have a relationship between sigma 1 and sigma 3. Now, you know the value of sigma 3 in this zone, and using this expression you will be able to get the value of sigma 1 in this passive zone. Now, come to the active zone. Again, here in this case you will have sigma 1 and you will have here as sigma 3. So, this is sigma 1 and here you will have sigma 3. So, what Bell's approach says that sigma 1 of the passive zone becomes equal to sigma 3 of the active zone. So, sigma 3 of the passive zone is known to me. I can find out sigma 1 of the passive zone. Now, this sigma 1 will become equal to sigma 3 of the active zone. So, this sigma 3 of the active zone now would be known. So, here let us say this is zone 1 and this is zone 2 that I am representing. So, what will happen is sigma 3 of zone 2 will become equal to sigma 1 of zone 1. So, this we have already obtained, therefore, we know this. Now, after knowing this, and we know that this rock mass is following this expression, that is sigma 1 is some function of sigma 3, then here we know sigma 3, and using this expression we can obtain sigma 1 in the second zone, that is the active zone. Now, this sigma 1 in the active zone is going to give us the ultimate bearing capacity of the foundation, sigma u. So, that is what is the concept of Bell's approach. Take a look once again. In the passive zone, we know what is sigma 3. Say in this case it is gamma z. We can find out sigma 1 of this zone. Now, sigma 3 of the active zone becomes equal to sigma 1 of the passive zone, and using this relationship between sigma 1 and sigma 3, we can find out sigma 1 in the active zone, and that is what is going to give me the ultimate bearing capacity of this strip footing. So, the problem is to define the lower bound bearing capacity of the foundation, and the solution can be obtained in this particular fashion, that is Qu ultimate is going to be Cr into NCS. This is going to be equation number 1, where this NCS is the bearing capacity factor. Now, how to get the strength? So, because here we are dealing with the rock mass, so we will have to get the strength in terms of the rock material and the discontinuities. So, let us say that we take a very simple example and use this Bell's approach and try to get the bearing capacity of this shallow or the strip foundations. So, in case of this strength of the rock material, I assume that it is following the Moore Coulomb failure criterion, and therefore we are going to get this expression. Equation number 2, where what is this CR and phi R? These are of the rock material. Then the second component of this rock mass is the discontinuity. And for that, I can again write tau j as Cj plus sigma tan phi j, where this Cj and phi j, they are the properties along the plane of discontinuity. So, this is how we can find out the strength. Again, here an assumption is involved that these are following Moore Coulomb criterion. Otherwise, these equations 2 and 3, they will not be valid. So, let us now take a very simple case of a strip foundation which is resting on surface only. Let us take the case of surface footing. So, I take a simple case of the surface footing. So, say here you have the ground surface, and since I am considering a theoretical case of a surface footing, so this is how the footing is going to look like. And we need to find out the Q ultimate of it, and here, like in case of the concept with respect to Bell's approach I explained you, so I will have these two zones here. The width of this footing is say B. I take the two elements, one is just outside and one is in this zone which is like this. I am showing it little bit bigger element, but these are the small elements. For the clarity I am drawing it little bigger. Now, in case if you have the discontinuity like this, which is making an angle of say theta, now this is here sigma 3 of this zone 1, and since this is the surface footing, so this sigma 3 of zone 1 is going to be equal to 0 because there is no overburden, and here we will have sigma 1 in the zone 1. So, basically this is what is my zone 1, and here this is zone 2, and obviously this one will also be zone 1. So, here we have sigma 3 of 1, and in this direction here this is going to be sigma 1 of the zone 1. Now, come to this zone 2. So again here we have this discontinuity which is at an angle of theta. So in this case here we have sigma 1 of zone 2. Let me write it with more clarity here, sigma 1 of zone 2, and here we will have sigma 3 of zone 2. Similarly, here also we will have sigma 3 of zone 2. So, as per the Bell's approach, what it is going to be, that sigma 1 of zone 1 would be equal to sigma 3 of zone 2, and from here I will obtain sigma 1 of zone 2, and this is what is going to be the value of the ultimate bearing capacity. Let us see how we can do that. So, first we will calculate the strength of material in zone 1. So, I write it as part A, that is calculate strength of material in zone 1. Now the first one is going to be the strength of the rock material, because it is the rock mass. So rock material and the discontinuity both will come into picture. So first we deal with the strength of the rock material, and this is what that we are going to get sigma 1 r in zone 1. This is going to be sigma 3 of zone 1 tan square 45 degree plus phi r upon 2 plus 2 cr tan of 45 plus phi r upon 2. Now in this case your sigma 3 in the zone 1 is going to be 0, as there is no overburden. So what this equation will give us is sigma 1 r of zone 1 is going to be equal to 2 cr tan of 45 plus phi r upon 2. This equation I will make it as equation number 4. Now this was about the strength of the rock material. Now let us try to find out the strength along the discontinuity plane. So I will have the second part of it, that is strength along the discontinuity plane. This is going to be the function of theta with respect to phi j. You recall we discussed about the single plane of weakness theory. So that's what I am going to consider here once again. So let us say that if phi j is greater than or equal to 90 minus theta, what does this signify is that the failure occurs in the rock material only. Please recall our discussion with respect to the theory related to single plane of weakness. There I explained you that when the failure will occur in rock material and when the failure will be there along the discontinuity. So in this case, when the failure occurs in the rock material, the strength of the discontinuity will be given by equation number 4 that we derived just now. But in case if you have phi j, if this phi j is less than 90 minus theta and less than 90 degree, then in this case the strength of discontinuity will be given by sigma 1 j in zone 1 will be equal to sigma 3j of zone 1 plus 2cj plus 2 sigma 3j1 tan phi j divided by 1 minus tan phi j divided by tan 90 minus theta multiplied by sine of 290 minus theta. This expression we have already derived when we were discussing about the single plane of weakness theory. There it was in terms of beta, and here we are considering the angle theta, but it is one and the same thing. Now in this case, since sigma 3j in the first zone is equal to 0, so this is going to give us sigma 1j in zone 1 as 2cj divided by 1 minus tan phi j divided by tan 90 minus theta into sine of 290 minus theta. This is how that we are going to get, because this term will become equal to 0. So I will mark this equation as equation number 5. Now this is what was there in zone 1. So now let us see that what will happen to zone 2. But before that, here we are considering only one plane of weakness, but in case of the rock mass you can have more number of discontinuity planes. So how to tackle such situation? So I have a third case here, that as the number of discontinuity planes or maybe you can say that these are the joint sets can be more than 1 and each may have their own Cj and phi j. So each having its own Cj and phi j. Then what we will do? In this case, what we are going to do is we will compute the values of sigma 1 j in zone 1 for each joint set. And then the fourth step is going to be that the strength of zone 1 will be defined as sigma 1 of zone 1 will be minimum of sigma 1 r of zone 1, that means the intact rock, then sigma 1 of say first joint set in the zone 1, sigma 1 of the second joint set in zone 1, and so on, sigma 1 of ith joint set in zone 1, and so on, sigma 1 of the nth joint set in zone 1. So, whichever is going to give you the minimum value, that is going to be defined as the strength in the zone 1, where this capital N is giving us the number of the joint sets. So, I will make this equation as equation number 6. Now, this was about the strength of zone 1, and this is how using equation number 6 we can determine what about in zone 2. So, the next segment comprises of the calculation for the strength of material in zone 2. Now again we will say that we will have the strength of the rock material and strength of the discontinuities. So in case of the zone 2, sigma 3 of zone 2 is going to be equal to sigma 1 of zone 1 as per the Bell's approach, and this one we have obtained already by equation number 6. So, this is known to us now. So, let us go to the next step and try to get the strength of the rock material in zone 2. So, what we are going to get is sigma 1 r of zone 2 will be equal to sigma 3 of zone 2 tan square 45 plus phi r by 2 plus 2 cr tan 45 plus phi r upon 2. Make it equation number 7. So, here sigma 3 is no more 0 as it was there in case of the zone 1. Now, let us try to get the strength of the discontinuities in the second zone. So, we have the third step for the evaluation of strength of discontinuity. Now, in this case again, if this phi j is greater than or equal to theta, then failure occurs in the rock material, and therefore the strength of the discontinuity will be given by the equation number 7 which we just derived. However, if you have phi j less than theta less than or equal to 90 degree, then in this case your strength of the discontinuity will be given by sigma 1 j of the second zone will be equal to sigma 3 j for the second zone plus 2Cj plus sigma 3j of the second zone tan of phi j divided by 1 minus tan phi j divided by tan of theta into sine of 2 theta. You need to be careful when to put theta and when to put 90 minus theta. If you recall the single plane of weakness theory, the beta angle we took from the major principal axis direction. So that you need to keep in mind when you are applying it here. Then what we need to do as a third step in this sequence is we need to repeat these calculations for n number of joint sets by considering the respective set characteristics, and ultimately we will find out the strength of zone 2. That is going to be sigma 1 comma 2 will be equal to minimum of sigma 1 r of zone 2, sigma 1 of the first set of the zone 2, then sigma 1 of the second set of the zone 2, and likewise sigma 1 of the ith set of zone 2, and so on sigma 1 of the nth set of zone 2. Make this equation as equation number 9, and this is what is going to give us Q ultimate. And here you can see that there is no limitation on the number of joint sets in the rock mass. So we can have as many number of joint sets as it is there in case of the rock mass. So this is how you will get the strength of zone 2. So therefore our Q ultimate would be CR into NCS. That was the first equation that we wrote. So from here this NCS is going to be Q ultimate divided by CR, and this is going to be sigma 1 of zone 2 divided by CR, and this is the function of Cj, phi j, theta, n, Cr and phi r. So from here the bearing capacity charts of NCS versus theta for different parametric values of Cj, phi j, Cr and phi r can be obtained. And once you have this these readily available charts with you, you can directly use this expression in order to obtain the Q ultimate. Now let us take another example till now the rock mass was following the Moore Coulomb failure criteria, but let us say that it follows the Hook and Brown criteria. Then what you will do? And in this case, say it has this overburden which will be equal to gamma into z. So what we have here is sigma 1f prime is equal to sigma 3f prime plus sigma ci mm sigma 3f prime divided by sigma ci plus s to the power a. This is what is the Hook and Brown criterion, where this mm, s and a, these are Hook and Brown parameters, and sigma ci is what? It is the UCS of the intact rock. So in this passive zone, what we are going to get is sigma 3f prime will be equal to gamma times z, or since we are writing in terms of the effective stresses, say I will write it as gamma prime. So sigma 1 f prime is going to be gamma prime z plus sigma ci mm gamma prime z upon sigma ci plus s to the power a. See, the parameters of Hook and Brown parameters, they will be known to me, and knowing this overburden and therefore sigma 3f prime, from here I can determine this in the passive zone, that is sigma 1f in the passive zone. Now what will happen in case of the active zone? Your sigma 3f prime would be sigma 1f of the passive zone. So that will be gamma prime z plus sigma ci mm gamma prime z upon sigma ci plus s to the power a. Now from here we can obtain the sigma 1f prime again using the Hook and Brown criterion, and this is what is going to give us the Q ultimate or sigma u, that's the ultimate bearing capacity. So this is how, using the Bell's approach, you can find out the ultimate bearing capacity of the foundation. Here we took a case of the strip foundation, and I tried to show you with the help of Moore Coulomb criterion and Hook and Brown criterion that how the procedure can be adopted. So there are various other methods that we can find out the bearing capacity of the shallow foundations. So we will take up some of these methods in the next class. Thank you so much.